we talk about the frequency, we also talk about time period of oscillation. So here is an interesting interesting information about something called longitude price. Okay, so there was this challenge, given to a scientist, really not necessarily a scientist, given, there was this challenge. In that challenge, a person is supposed to be able to develop an accurate timekeeping device. We just talked about the period, right? So timekeeping device that can also handle the change in the pressure, change in the temperature, change in the humidity. So, people who are traveling through the sea or ocean, they can keep track of longitude, east-west position. Okay, so longitude, right? I mean, it's like this is, let's say, north, south, east, west. So longitude is this, right? Okay, basically. So longitude. Okay, so the mariners can keep track of the longitude based on the change in the pressure, change in temperature, and change in humidity. So there was this longitude prize given by British Parliament, which was worth about 4 million today for this solution, and who got that is the interesting thing. Okay, so it turns out that this person here, John Harrison, who was born in 1693, died in 1766. He was actually not a scientist. Okay, he was a English carpenter and a clockmaker, and then he invented the marine chronometer. So there is also the book here. You could look at here, Longitude, the true history of lone genius who solved the greatest scientific problem of his time, from New York. So it was John Harrison who solved this. He was this, carpenter and clockmaker, and who solved this problem of who invented the chronometer. Okay. All right. Next topic. Where did I keep my marker? Okay, it's here. So we are looking at oscillations so far. We didn't talk about anything called damped. Okay, so now next topic is going to be damped oscillation. Damped oscillations. And simple harmonic motion, because that's our topic, right? How are they related? So what kind of oscillation is called damped oscillation? Before we do anything, I'm going to just try to show you guys the spring mass system and see what happens here. Same spring mass system, we had it last time. Let's look at this. Okay, so let's look at for a couple of, maybe for a minute. I don't know if I can hold it for a minute, but let's see. It's kind of, let us see. Can you guys see this? You should be able to see it up here. Okay, so I'm going to put this over here. Okay, now it is in oscillation. See, it's no longer in oscillation. Let's try again. Oh. So, this kind of oscillation, where the oscillation dies out. See, it is oscillating, but it dies out in time. And then it stops almost oscillating, or there is very tiny oscillation. This kind of oscillation, which dies out in time, is called damped oscillation. Okay? So there is still a repetition, right, of the oscillation. However, there is still, the system is still oscillating. However, as the time increases, it dies out slowly. All right. So this kind of oscillation is called damped oscillation. So damping could die out due to the friction in the system, due to the air resistance, due to other phenomena. Okay. And it turns out, if we want to, I'm gonna put it over here. Maybe here. I don't want this to. Alright, so look at this position here. It's very similar like the one we had for a spring, right? It starts from some amplitude, right? It has a maximum. This zero line corresponds to the equilibrium position. It goes down, all the way down, goes up. But you see, this look at this length here. From this zero line or equilibrium position to this, peak here. See, this height is decreasing every time, decreasing. That's what it means. So every time, if we leave it, we just saw that, right? Oscillation. If we leave that oscillation of a spring mass system, the amplitude decreases, in time, right? And then that decrement also tells us that it's a damped oscillation. Okay, so this is the graph we have here for position versus time graph for damped oscillation. Now, how might we model this mathematically? Have you guys seen anything like this before? What kind of equation could we use? That's what we are saying, right? What kind of equation would be appropriate to this, right? Or how might we model this mathematically? Could we just use, it also starts from here, so it must be the cost, somewhere there should be the cost, right? We could say, okay, but then it's not quite just cost function like we had before, because before we had what? Xt equal to a cos 2 pi ft, right? But then we cannot quite use this because that was, in that case, this amplitude was not dying, this was constant, right? Here the amplitude is dying. This A must decrease as a function of time. So we have to find a way to say that, wait, this amplitude became this small and then it became this small in certain period of time. So we have to tell that. So how might we model this mathematically? We know there has to be cost somehow because the graph is still like this, right? Graph is kind of like this and then it's like this, so it has to have somewhere cost, so we know that much. It will also have an amplitude because that's also there, but that A must decrease by some factor, so something here has to multiply that so that the amplitude, so that we can make sense saying that the amplitude decrease as the time increase, meaning, I don't know, something here, x, maybe something, okay, x means, maybe no, I don't want to write that, it will confuse you guys, position there, I want to write y, something, and it decreases, so somehow there has to be decrement, which means negative, and somehow there has to be time t, negative sign, time, and then combination of some of these things has to tell us that, okay, we have to be able to model this graph mathematically. So take a moment, give yourself a moment, see if you can do anything about it, or you can come up with something. Alright, so I'm going to show you guys here, okay. So we cannot use this equation. How? Because we need more information to include here. This has more information than the other one. So it turns out that we can model this equation, this graph, using this mathematical equation here. I'm going to write this down because we'll be using this more. Xt equal to amplitude e to the power minus t, meaning amplitude decreases as a function of time t by tau. I'm going to talk what the tau means, and then cos of 2 pi ft. Okay, so see, this part is different here. This part is introduced to indicate damping in the system. Okay, so we had the same spring mass system earlier, we looked at it before, we didn't talk about the damping. And then if there is no damping, meaning it's really ideal, right? Like there is no friction or nothing there, then it would be just a cos 2 pi ft. However, because there is a damping, the oscillation is going to die out as a function of time. So we have this e to the power minus t by tau. Okay, so t is time, tau is, so a is amplitude, okay? A is amplitude, tau is called time constant. Okay, this is also called characteristic time. This tau will really tell us how much of the, how fast this, damping occurs, okay? So this is, tau is the time constant. So this whole equation, anytime you see some equation x equal to a e to the power minus t by tau, or y equal to, okay, I'm just writing here as a general. This is really called the time decay equation because this e to the power negative means it decays, right? It goes down with the time, okay? So this is also, you could also call this time decay, okay? This equation, actually, this model is not just applicable here, it's also applicable in nuclear physics, really, okay? So there are many applications of this type of system in physics. So what is this E? You guys may be wondering. She's writing all these, but I have no clue what that E is. E is exponential, okay? E has the value. Remember, do you guys remember? E is 2.718. Okay, so that is the constant. What else here? Okay, so just looking at here, let us look at I'm not gonna write this down here yet, but I just want to tell this out. At time equal to 0, t equal to 0, where do we have this graph here? It's at 0. If you guys cannot read, I'm gonna read this out here. So this graph, it starts at 0, there is a 1, 2, 3 seconds and so on. On the x-axis, on the y-axis, it starts at 0, and then the division goes by 0.01, 0.02, 0.03, all the way to 0.06 here. So let's say at t equal to 0 means when we are at the equilibrium position right here. What happens here in this equation? Amplitude at t equal to 0, at time 0 we have a maximum amplitude, right? So a should be there, but t is 0, so this quantity should not be there. It should just become 1, right? Something to the power 0. And then cos, and then we also have a t here, so this whole thing also is going to go to 0. So cos 0 is 1. So basically x at t equal to 0 is a, which is correct, right? So it's maximum here. Alright. So okay, so that's the important thing. And then this tau is a time constant. This tau really tells us how quickly this oscillation is going to die out, the rate at which this oscillation dies out. That's what the time constant tells us. Okay, so let's see, let's try to do a few things here, a few okay. So I'm gonna leave out that equation there, and then sorry about that. Okay guys, so here is an example for damped oscillations. You're given the following graph of damped oscillatory motion. Determine the frequency and the time constant. So we are asked here f equal to what, and then tau equal to what. Some of you guys, I already told you, I'm going to draw this here. Maybe if you are not able to see it, in the video, let me just draw this out here real quick. This is time in second. We have a position x in centimeter here, this direction. This is our 0, 1, 2, 3, 4, 5, and so on. And then on the other side we have, so this is a 0.1, 0.01, okay, and then 0.02, 0.03, 0.04, oops, this is gonna be really back here, 0.05, all the way to 0.06. Our graph starts here at 0.05, this point here, and then it goes all the way to, I also need to make it down here also, minus 0.01, minus 0.02, minus 0.03, minus 0.04. Yeah, that's enough. You can do more with 0.05 and so on. It goes all the way to 6 there. That's okay. Okay, so this graph here, it starts at this one, goes all the way. So I'm just going to make a dot and then connect it, okay, so that I don't have to keep making the curve again to fit it. And then it goes all the way almost up to, almost, not quite, almost up to there. And then by the time it gets here, it gets around 0.0, it gets almost in between there. And then the other one is about 0.02, so it goes, and then it goes here about 0.02. So okay, like that. Okay guys, so here graph goes like this. Oops. Alright guys, it didn't, I want it to be more smooth, not like that. Okay. Oh, here let me write this. This is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. So almost here, it goes, oh, I just erased that part that I really needed it. That is needed. 5, that here, okay, so it goes here, and it kind of curves back here, okay, so I'm going to just draw only this much. It has more here. I'm also going to put it here, over here for you. I don't know where, I guess here is fine. Alright, so you're supposed to find what's the frequency and then what is the time constant tau. So take a moment, give yourself a minute and try to see if you can find this out, okay? Alright, I'm gonna show you guys the steps in the next video, okay, about how to find the frequency and the time constant for the given graph.